So this question again concerns calorimetry and the application of law of conservation of energy to find the missing variables. It could be specific heat capacity, mass, etc. Right. So let's look at what it's saying. A calorimeter for which MC, right? So instead of giving us just C, it is directly giving us the mass multiplied by the C, right? So that makes our life easier. We have to take notice. The MC directly is given 25 joules per Kelvin. As you can see, the kilogram inverse is missing, which means they have already multiplied the mass and C for us. That makes our life easier, right? Contains 140 gram of liquid, right? So this calorimeter, which has the MC of this much, contains some liquid, which is 140 gram, okay? An immersion heater is used to provide energy at the rate of 40 watts for a total time of 4 minutes, right? So there is a heater here, which is going to provide us the Q, right? It has a wattage 40 watts and it works for 4 minutes. Okay, so we can very easily calculate how much the Q will be given, right? By doing some multiplication. So Q is also known to us in this case. The temperature of the liquid increases by 15.8 degrees Celsius, right? So they're directly giving now delta T as well, right? So not the initial and final temperature, but the change in temperature directly given. So 15.8 degrees Celsius, and that is going to be also equal to 15.8 Kelvin. Okay. So calculate the specific heat capacity of the liquid and state the assumption made to reaching the result. So assumption is that basically no heat is lost, right? So if the no heat is lost, basically the law of conservation of energy will guarantee that whatever heat is coming into the system is used by this, right? So first let's compute how much heat actually enters the system, right? So we're going to compute the Q. Q is going to be 40 watts per second for 4 minutes, going to be 4 into 60, and that is going to be 9,600 joules. Okay, so now this 9,600 joules is going to come into the system. First, it will be consumed by the calorimeter itself. Okay, because it is covering the liquid and then the liquid. Okay, and some of this will be 9,600 joules. Okay, so for calorimeter, MC is already known, and we now know the delta T, right? So the calorimeter will consume basically 25 multiplied by 15.8 joules, right? Pretty straightforward. And that will be how much? 395 joules. Okay. For the liquid, we now know the mass, which is 140 grams. So we have to always convert it to kilograms. So this is going to be 0.14 kilogram, right? And C is unknown. So we'll say 0.14 multiplied by C into delta T, which is 15.8. Okay. So now 9,600 joules of energy is coming, of which the calorimeter is going to take away 395. So we are going to end up with 9,600 minus 395 joules, right? And that is going to be equal to roughly around 9,200 joules. Okay, so we call it 400, so roughly around 9,200 joules. And that is also going to be equal to 0.14 into C into 15.8, which is the heat consumed by the liquid. From here, we can simply calculate the C. Our C is going to be 9,200 divided by 0.14 divided by 15.8, right? So nothing complicated there, roughly 4159 joules per kilogram per Kelvin. If you want to write it something like 4.1 into 10 to the power 3 joules per kilogram per Kelvin, and that is going to be our answer.